Oh, we're three guys. We're gonna talk about two metals and one alloy. First, we're gonna talk about copper. This is the stress strain curve for copper. The elastic modulus is the slope on the elastic region of the curve. As you can see here, highlighted in green, that is the line that we've used to find the elastic modulus. We use the equation stress equals elastic modulus times strain, and the yield point, which in this case is 33 megapascals and 0.003 strain. And using this, we find that the elastic modulus is 110 gigapascals. Next, the yield point. Here we see the yield point right here circled on this red dot. Like we said before, the yield point is 33 megapascals at 0.003 strain. This represents the strength required to make it so the metal enters plastic deformation. Next, we have the tensile strength. This is the peak strength of the metal. After this, it goes down until it eventually breaks. As we can see for copper, it is 210 megapascals. Next, we have the ductility. This is the percent elongation or the total strain at the fracture point. As you can see right here, circled right there is the breaking point. And as you go down, you can see that at 0.6 strain is where it breaks. So that means that ductility is 60%. We have the resilience. It is the total area under the elastic curve. In this case, we can see that it is 49,500 pascals. And to get this, you can do the area of a triangle, which is 1/2 base times height, which you use the coordinates of the yield point for the base and height. Next, we have the toughness of the curve. This is the area under the entire curve, including the resilience. So you find this by adding the resilience to the rest of the area under the curve, which you can use doing integration or finding the area of shapes like trapezoids under the curve to approximate the total area.
So for our second metal, we're doing grade 1 titanium. This is the stress strain curve for titanium. For the elastic modulus of titanium, we use the equation stress equals elastic modulus times strain. And as you can see on the stress strain curve, the elastic modulus is the linear part of the curve, highlighted in purple. The yield point is 240 megapascals at 0.002 strain. And using this equation, we figured out that elastic modulus equals 116 gigapascals. For the yield point of titanium, you can see that when the stress strain curve stops being linear, it is representative of the strength of titanium. As said before, the yield point is 240 megapascals at 0.002 strain. And looking at the stress strain curve, we figured out that the strength of titanium is 240 megapascals. For the tensile strength of titanium, this is represented as the peak or max stress. As represented on the stress strain curve, it is the point after it stops being linear and it heads towards the breaking point. We figured out that it's equal to 330 megapascals. For the ductility of titanium, it is the percent elongation and the total strain at fracture. As you can see on the stress strain curve, the breaking point occurs at 0.3 strain or 30%. Resilience is represented as the area under the linear or the yield strength. So at the point of yield strength, use the coordinates and find the length and width of this triangle and use the equation base times height. And we figure out the resilience is 240,000 pascals. The toughness of titanium can be found by using the area under the entire curve of the stress strain curve. You can add the resilience plus the rest of the area using area approximation.
Titanium copper alloy. In this alloy, we have titanium and 2.5% copper. Here's the graph, the stress strain curve graph for this alloy. As you can see, the strength is much higher than the previous metals. The elastic modulus is found the same way as the other two metals, and here we can see the linear line highlighted in pink. And the yield point is 480 megapascals and 0.0046 strain. And using the formula, we found that it's 105 gigapascals for the elastic modulus. The yield point for this curve is 480 megapascals and 0.0046 strain. So the strength is 480 megapascals. Tensile strength is found at the peak of the curve. We found this to be 620 megapascals. As we can see with this alloy, it is much stronger than the other two metals, and this is a common theme among most alloys. Ductility for this alloy is seen to be 0.24 or 24%. This is the total strain up until the break point. As you can see with this alloy, it is much less ductility compared to the metals. This is also a common theme among alloys. In the yield point that we saw earlier, we can find the area under the linear or the resilience. And using those coordinates, we found that it is 1,104,000 pascals. Or the toughness is found using the area under the entire curve. So this whole area right here. So this includes the resilience that we found earlier, and then the rest of the curve. As I said before, you can find the rest of the curve using area approximation or an integration if you know a formula.
You're given the question that 1 meter of cylindrical specimens of your metal 1 and metal 2, which in our case is copper and titanium, that has a diameter of 20 centimeters, is pulled in tension with force of 4 kilonewtons. What is the change in length and width experienced by your specimen 1 and specimen 2? So the first thing we can notice is we noted that the radius is equal to half of the diameter. We're given the diameter is equal to 20 centimeters. Therefore, the radius is equal to 0.1 meter or 10 centimeters. From that, we can find the area. Area is equal to pi r squared. So plugging in our numbers, we get the area to be about 0.314 meters squared. Again, we know the force is equal to 4 kilonewtons. Converting that into newtons to get to our base unit, we find that our force is equal to 4,000 newtons. Knowing that sigma is equal to force over the area, we're able to calculate our stress for sigma, which in this case is 127,324 pascals. So here we can see that our stress is equal to 127,324 pascals, which we calculated on the last slide. Our next step would be calculating epsilon, or the strain. We know strain is equal to sigma over E, Young's modulus. Plugging in our knowns, we get our strain to be about 0.00012%, which from that answer we can find the change in length by plugging into the equation epsilon sub L times L is equal to the change in L. Our next step would be finding epsilon sub W. Epsilon sub W is equal to negative V epsilon sub L. V is known as Poisson's ratio, which in this case for copper is 0.343. Calculating that out, we get our epsilon sub W to be about negative 3.97 times 10 to negative 7. Again, using the equation, change in W is equal to epsilon sub W times D, we're able to find our change in width. We can repeat the process on the previous slide and observe our answers for change in L and change in W. Notice that the answer for change W, same as on the last slide, is a negative, meaning that the width decreased with the tension. Lastly, these are our sources where we got all the information for this presentation.